other star, one other helium Ceres had a p-dot measurement. That's HM Cancri, and it's got an orbital period of about 5 minutes. It's the fastest one that we know of. And several independent 4-year baselines have all indicated a negative p-dot, that is a shortening period of about 1 part in 10 to the 11. I'll comment further on that when I have the context. So here's our result. Here's our result for an 18-year light curve on AM10 where I resized the dots to give you an idea of the error of each individual measurement. And I want you to have a chance to see it with unbiased eyes, so I wanted to show it to you bare before I overlay any models. This is plotted relative to a test period of 1028.7322 seconds. And here's a straight line, just to keep in mind there. There's a straight line, and here is the least squares best fit. It is a shallow concave down parabola, and it gives you a p-dot of -4 times 10 to the -13, the plus or minus 3, the coefficient. To remind you, this is a shortening orbital period. And to give you, I think this might answer your question, Adam, to give you an idea of this, well, what does that mean? What would happen if you had a parabola that went through the highest point in the scatter? The parabola that goes through the highest point in the scatter is -4 times 10 to the -12.
Well, I guess what I'm interested in is what is the chi-square method? Is that really the optimal fit for that data?
This is the optimal fit for the data. The chi-square, I don't know what the chi-square is.
Yeah,
But to know the chi-square, you need to know the errors on the data points.
yeah.
So I mean,
Well,
that's,
she's
The
saying
errors
that
on
the
the
errors
data
are
points,
They're
yeah.
the size of the dots.
They're about the size of the dots. They're
Well,
little.
so the chi-square is enormous.
Well,
Yeah,
Right.
so that
Yeah.
suggests the errors are underestimated.
yeah, that would be the obvious.
Yeah,
Now,
the
it's hard to
scatter
know what
is
the
way
errors are,
more.
because you have to subtract
Yeah.
a couple of powerful signals to get to the orbital signal. And the waveform is not a pure sinusoid.
Yeah.
So not even all parts of the waveform contributes to the depth. So you really can't find out what the error is, and that's why the scatter is probably the best definition, approximate definition. This is when if you study cataclysmic variables, both of the words just tell you, don't ask what the errors are.
If that's true, then I don't understand the origin of the error.
Yeah.
3, how can you know?
I took that, well, maybe this wasn't the best way to characterize it. It was the way that made most sense to me. What I did was, I plotted a whole bunch of parabolas, and I got a sense of how different from 10 to the -13 a parabola that goes through, for example, the parabola that goes through that highest point is. I don't know if I'm saying that in very good English, but that was how I got a handle on how good a fit that really is, how significant a number that is.
but isn't,
Now, but wait a minute, while I remember, I'm not saying that we understand what the system is doing. I'm just saying that this is the best fit to the data that we have. And I'll talk more about what the
For this
system might be
particular
doing.
model, is for a constant p-dot
Yes.
model.
Yes, yeah.
With
We're
the
assuming
perfect
P double dot is
subtraction
0.
of humps and
Well,
super humps and all that
That needs
jazz.
to be folded into the uncertainty.
Yes, that's right.
I mean, looked at from the point of view of data analysis problem, you've got these plots and you're fitting as you say, a second order polynomial. So you have errors in the coefficients of that polynomial, I mean, fitting errors. So I think those are the things that should be, I mean, there's a fitting error to p-test and to p-dot, and there are 3 coefficients I suppose. So I mean, it's a linear fitting problem. It's not as if it's non-linear or peculiar in some way. So if you're saying that the scatter is contributed by random errors, then those
It's a systematic problem with, so this system, when you look at the power spectrum, you don't have a clear view of the orbital signal. It's got a very close, stronger orbital sideband, you gotta subtract that off first. And so you also need a long enough baseline to get significant frequency resolution. But if your baseline has a large gap in the middle, you have a huge aliasing problem. So I wouldn't characterize that as random. That's just
But I mean, the arrows on these points from one to the other are not correlated.
They're all independent.
They're all independent.
They're independent. data points.
Independent, is what I
So
mean.
therefore you can do a fed,
They're
it
independent
means something.
estimates on the timescale. So,
But- Well, you can talk about an RMS, a root mean square, you can't talk about a Gaussian error because you don't get a decent chi-square.
Well, I mean, that simply says that that model is indicating there's something wrong. I mean,
Well, no, it's more indicating that the error bar, the systematic error bars on those points are much larger than shown here.
But what you could have
systematic
done,
or they're there, whether they're systematic or random, they're there.
but what you could do is put the error bars on each point from the scatter in a region there.
Exactly.
And that would be the way I would say the error, and which the error is like 0.2 on that scale. And so I would redo your number fitting error of 0.2, and you get that is not a, you get it's -4 plus or minus something big. And
Yeah.
It's consistent with nothing.
Well, let her go on, I don't believe she's gonna claim a detection of a negative
I'm
p-dot.
not, I'm gonna make a very conservative claim here.
Yeah, no, he's not squibbling with that, it's just that, you know, the scatter of the points is sort of the best available measure of, so,
That's all I'm saying.
there you go.
Although, not to belabor, it's a little misleading because this may not be the right model for this star.
Oh, yeah.
Why don't I
So-
talk about this in
yeah.
context
Could
of
be
the
a planet
current
that
models
goes
that are
up
out
and down
there?
100 times.
Exactly.
Okay, going on.
All right. All right, so what should we expect to find? If you take the requirement that the secondary fill its Roche lobe, and you couple that with Kepler's law, you get this relationship at the top there between average secondary density and period. Then you get this second equation relating p dot to zeta, where zeta is the mass radius relation, d ln r2 over d ln m2. And m2 dot is the mass transfer from the secondary. And so at zeta equals 1/3, you get this period turnaround. Now, what does that correspond to in terms of actual time? One evolutionary calculation has been done. It gives a period minimum of about 10 minutes. And I want to explain to you what that means. So this curve, this is the trajectory of the secondary from 0.6 solar masses, these are in solar mass units. It's done burning helium, and it is cooling off, and it is crossing this boundary in log-log plot of the density of central density and central temperature. And that line represents equal contributions to the pressure from degenerate electrons and thermal motions. And if you start off with a 0.6 solar mass secondary and give it some other initial parameters, it will cross this line around 10 minutes. But a lot of assumptions go into where that curve crosses the boundary. If you ask, well, okay, so when does degeneracy begin to dominate the evolution? It depends primarily on the birth channel of the system. Where did this thing come from? What was the secondary long, long ago before Roche lobe overflow? If it was never massive enough to ignite helium in its core, maybe it is a fully degenerate helium white dwarf at the onset of Roche lobe overflow. Or maybe it ignited helium and it's still burning helium at Roche lobe overflow. Maybe it's just about done burning helium at Roche lobe overflow. Maybe it's long since finished burning helium and is now a fully degenerate carbon white dwarf at Roche lobe overflow. Now, all of those potential birth channels set different values for the initial secondary mass, the mass transfer rate, the temperature of the core, the composition, and the orbital period at the birth of the system. and all require a double common envelope phase to be born, which it doesn't seem like we've figured out how to make happen at all. So, it seems as though we need to work on this model. Meanwhile, oh, I'm sorry, let me point out that the period minimum of 10 minutes assumes that it's still burning helium at Roche low overflow, and it assumes one value of each of those other parameters, and not a range of possible values. And this is the only estimate that's been done.
So the fact that HM Cancri, or whatever the heck its name was, has a period of 5 minutes, does that mean it's most probably on the degenerate side, or you still can play with those numbers and get it on either side?
Well, if you take that, then HM Cancri, nothing should have a period of 5 minutes. None of them should. So it indicates that that number is just not a representative number.
Yeah, okay. So there's some other values, and they just need to play with their simulations and get a different set of numbers.
Yes,
Okay.
yes,
Or just possibly. HM Cancri
yes.
is not an example of this type of
Yes.
class.
HM Cancri, the spectrum, that when you look at the spectral lines, HM Cancri does not show double-peaked lines. Double-peaked lines are characteristic of the disk, but not all CVs show double-peaked lines. I'm happy to talk about that after done it. So I want to be fair. I don't want to only attack the model, attack our light curve as well. It's possible that we have not captured the true secular evolution here. By secular evolution, I mean intrinsic, long-term evolution of the system. Maybe we've captured a transient phase during helium burning evolution, and if we were to zoom out and look at it over a 60-year light curve, we'd see a completely different trend. But I want to point out that that's the number that we get from the least squares fit, the 2-degree polynomial. P dot equals -10 to the -12 or 13. That number is consistent with a system evolving via angular momentum loss due to gravitational wave radiation for a system with orbital period around 10 to the 3 seconds. And the same is true for the HM Cancri measurement. To remind you, the orbital period change in HM Cancri is -10 to the -11 or 12. That is consistent with evolution governed by angular momentum loss due to gravitational waves. So, for a system with that shorter orbital period, 10 to the 2 seconds. So, to summarize this, our pulse timing shows no evidence, no strong evidence, that this system is evolving towards longer period. Given the scatter, that is the strongest statement I will make about these data. In addition, the parameters of the evolutionary calculation are too narrowly chosen. So what do? Well, we can continue our light curve. We don't need to pay anybody any money to do that, so we'll keep doing it.
You observe for free?
Well, relative to
Backer.
you.
Nor do we get paid anything. It's fair.
Okay, that's fair. There are about 4 other helium CVs with orbital periods shorter than about 26 minutes. And we can continue monitoring them as well, doing the same thing in those systems. That'll take another 8 or so years at least to get a decent timing on those. And then spectroscopy has shown promising initial results of a method to determine birth channel. You look at the chemical composition, and that can be a clue to where these things came from. And future modeling, we need to do a more thorough modeling in terms of different birth channel and then what that predicts for composition, core temperature, and other parameters at the birth of the system.
When you do that spectroscopy with your MDM telescopes, or do you need big glass to do that?
Yeah. We can get chemical composition from the 2.4 meter, can't we?
Just the brightest of stars, most of the new anti-convent stars, the ones with emission lines, which is where you can do it,
Yeah.
are quite, they're about 20th magnitude.
Yeah, okay.
Yeah, they are.
Quite good. Do it with some other telescopes.
I don't know what, Nelmans is the one who's been doing this, and I don't know where he observes.
He just gets on the phone and whoever agrees to. He's never looked through a telescope in his life. He's very good on the phone. It's a great research instrument.
It's good to know. Okay, so, the key findings of this study are, 18-year light curve of Amkin-Ben shows no evidence for orbital period lengthening in the system. And might be consistent with evolution governed by angular momentum laws due to gravitational wave radiation, as is the case for ancient Cancri. Just to remind you of the first study, here it is, Joe. Wait. Okay. This snapshot of 10 helium CDs on an epsilon PR plot indicates that they are evolving towards longer orbital period. Amkin-Ben is the first dot on the left, and none of the other points have had pulse timings. I just want to juxtapose those two. Did you want to attack that further?
No, I just would like to meditate on it for a few more months, but we don't have time.
It's too late.
It's too,
That one's published. This one you have to
If you
wait.
can sharpen that conclusion,
I'm sorry?
if you can sharpen that conclusion, would you arrive at a test of general relativity radiation?
I don't think,
You don't have to
given
worry
everyone's
about-
quibbling about the scatter here, I don't think that I want to hold this up as a test of anything.
well,
Yet.
Eve's too modest to refer to this, but we actually have a point, 2 points actually. 13 years before the beginning here, which I did when I was in graduate school. And we took our data on paper tape. Anybody remember?
Yep.
The old timers. You remember?
I had one.
Oh, okay. Paper tape. And so in an effort to try to extract the reliable timings from the data on paper tape, plus my scribblings in my notebook on March 10th, 1978, well, I have 2 timings, and they actually are consistent with the downward extrapolation of that red line. But I'm really nervous about my confidence in whether I can get that right, after, given how many generations of media change have taken place since then. Because I did, as each new generation took place, I converted it to the new one, but there's a problem, you know.
So you have it on Blu-ray now?
No, I don't. I never even heard of that one. So anyway, redeeming the past is sometimes a substitute for waiting 10 years on the other way. Sometimes.
Okay, so in conclusion, I've discussed 2 studies that both aim to answer the question, what is the rate of orbital period change in these helium CVs? And more importantly, what is the secondary? What does a sun do when it leaves the main sequence? What does it do if you stick it in a binary and it leaves the main sequence? And so the distribution of 10 of them in epsilon p orb space, and this is 10 that shows superhumps, indicate that their orbital period is lengthening, and that suggests that the secondaries in these systems are significantly degenerate objects. And, okay, so next up, we want to continue, hopefully, embellish this tentative pattern by looking at more systems that show superhumps. We have limited ability to do this because the longer orbital period systems tend to very rarely show these outbursts, and you have to catch the systems in outbursts in order to measure them. There are about 7 more, though, that I think we can get measurements of. And the second study, pulse timing, direct pulse timing of one of these objects, does not support the picture of lengthening orbital period. And so next up for that, we want to work on the evolutionary model. We want to continue our light curve of Amkin-Ben and the other short period helium CVs. Finally, I'm not going to get to this today, but the other subjects of my dissertation have to do with signals associated with the accretion disk and whether disks and CVs can tilt. This is a problematic picture for CVs because it appears that the white dwarf, the radiation from the white dwarf cannot affect this tilt. And so it's unclear why tilt would be occurring. I am happy to answer questions about that if you're curious. So I would like to thank, I won't read everybody's name, but I would like to thank first and foremost Rick Rothschild and Joe Patterson. Also George Fuller, Hans Parr, Adam Bergasser, Barney Brickett, and Judy Kim, and Eric Mickelson. And my parents, Ellen and Peter Armstrong, my sister Sarah, my husband Wayne Yeager, and my friends Sam Selesnik and Philip Steig. Thank you all for listening.
Okay, do we have any questions from the peanut gallery? As those of you old enough to remember how to do the, anyway. Any questions?
You can leave that on.
Yeah, I'm just,
Which of the people you mentioned is the creeper?
The creeper is, no, I didn't mention that loud. The creeper is the never-before-seen creature who inhabits the 1.3 meter dome and will, if he likes you, ensure that the 1.3 meter works.
I think I actually saw that Scooby-Doo. But I also have a serious question.
Yes.
Which is, this isn't related to work in particular, but how do these like really tight white dwarf systems form? Did they start at like some reasonable orbital separation as like main sequence stars and like gradually decay over like an extremely long time, or did they actually like form close in like that?
No, so imagine, 10 to the 9 years ago, you've got two main sequence stars in wide orbit of years. Okay. One of them burns through its hydrogen, goes to red giant phase, and that red giant phase encapsulates these two stars. And the drag that this red giant phase causes is called the common envelope phase. That's what I've been meaning when I say common envelope. And so they spin, so their binary separation shortens. And that is the birth of so once the common envelope dissipates,
Oh,
It's just an ordinary envelope.
is that the prophet, what's his name used in the
yes,
Once that dissipates, you have a closed binary system. And that is presumably the helium CDs, where you've got a sun, and the one that went red giant is now the white dwarf. Presumably, though, if you want to make a helium CD, you've got to let the secondary do that too. And so that's going to create a second common envelope phase, and the binary orbit will shrink further. So I don't think I've made this clear. The double white dwarf systems, the most compact systems, are essentially two white dwarfs separated by several Earth radii.
That's small.
Yes.
Yeah.
Okay, yeah. Thank you.
Anybody else?
Yes.
You do keep saying that nobody knows how to make a double common envelope system. Why, can you expound on that? Why is that so difficult?
I'm talking about the simulations people, and I don't understand what it is they do. But from what they tell me, I infer that no one's really figured out how to get a binary system to survive two common envelope phases.
You can make it a merger instead.
A merger, or they're blown. Either you get a merger, or the common envelope. You know what? I don't really understand the physics of it, so I'm a little uncomfortable answering the question. But either get a merger, or there's no binary anymore.
Is you just get tidal forces to unbind the system? Is that what happens?
Could the red giant actually? What I'm thinking is.
You mean the second time? Is that- Yeah, I mean, I would guess that, I mean, obviously merger is one possibility, but the other one might be that the two stars ended up at separations. Now, they both lost their envelope and end up at separations such that GR won't grind them down
Yeah.
on an interesting time scale. Like if it was 10 hours
Right,
or
I'm
one
wondering-
day, that's too wide.
What I'm wondering is, can the red giant atmosphere actually cause the orbital separation to increase?
Yeah.
If you've got some tidal locking, you can do that.
You know, exhaust, some kind of secondary mechanism.
Or does the second envelope dump enough stuff on the first white dwarf to make it supernova?
So
No.
there's an angular sizes thing out there. 1AU is really small. So.
It's a very
You
small
could.
target.
But I mean, it was, one of the plots showed you were dumping like half a solar mass over time.
After
One-
contact.
Yeah, I'm
But,
saying,
you know,
oh, you don't have contact until the
No.
second envelope's done.
Yeah.
Okay.
But wait, when the first star evolves beyond the main sequence and becomes a red giant, a lot of that matter is accreted by what will eventually become the secondary. And if the secondary is close enough to, never mind, I'm sorry, I'm confusing myself. Initially, you have accretion one way, and then. What's the other way?
Anyone else? All right, well, let's thank the audience and, we